Hello, and welcome to this free course in Data Science and Machine Learning for Beginners, made by AI Sciences Academy. This easy-to-understand course is dedicated for beginners who need to learn the A to Z fundamentals of data science and machine learning through a gradual and segmented approach. Okay, here are the four main parts we will cover during this course. We will start with an introduction part to data science and machine learning. In this part, we will answer some questions that you may ask, like, what is data science and machine learning? Why data science now? And when I can apply data science and machine learning techniques. In learning part 1, we will learn the preliminary to understand data science and machine learning. In this part, we will learn some vital concepts in data science and machine learning. In learning part 2, we will start the machine learning part, where I will explain to you how the machine learning models work. We'll also discuss about regression, classification, and clustering. In learning part 3, we will talk about how to evaluate the performance of the model and choose the best one based on some indicators. In learning part 4 of this course, we will discuss about some best practices in data science and machine learning. At the end of this course, you will receive a gift, so please follow this course until the end. This gift will help you on your learning journey. So, ready? Let's start. Data science is not a straightforward, easy-to-define field like most traditional fields. It's rather a multidisciplinary field, which means that it combines different areas, such as computer science, mathematics, and statistics. Because data science can be applied and used in various applications and fields, it requires domain expertise in each particular area. Okay, for example, if we use data science to develop a medical analysis application, then we will need an expert in medicine to help define the system and interpret the results. Data scientists explore the data, visualize it, and calculate important statistics from it. Then, depending on these steps and the nature of the problem itself, they develop a machine learning model to identify the patterns. So, machine learning and deep learning are the subfields of data science. So, you might ask, what is the difference between data science, data analytics, and big data? Well, big data means huge volumes of various types of data. We differentiate big data by its 4 V's, which are the characteristics that are distinct from ordinary data. They are volume, velocity, variety, and veracity. The sheer volume is the main characteristic that makes data big. Velocity is the frequency of incoming data that needs to be processed. Variety means different forms of data. Veracity refers to the trustworthiness of the data. On the other hand, data analytics is more about extracting information from the data by calculating statistical measures and visualizing the relationship between the different variables and how they are used to solve a problem. It's like descriptive statistics. Why data science now? That's an interesting question. First, there is currently plenty of data, more than at any time before in history, and it just keeps growing exponentially. Second, now we have much better computers and computational power than ever before. A task that can be finished in a few seconds nowadays would have required days with the computers that existed just a few years ago. And finally, we have more advanced algorithms for pattern recognition and machine learning than we did just a few years ago. So, in one sentence, if you want to know why data science has become our focus right now, it is because we have a lot more data, better algorithms, and better hardware. Let us see where data science and machine learning is applied. I want to say that data science is everywhere. The number of data science applications is countless. It is because we have data everywhere, and there are dozens of algorithms developed each year to solve these tasks. However, we will talk about a few famous use cases of machine learning and data science in our daily lives. As you can see, machine learning and data science are currently being used in many fields, such as healthcare, finance, transport, social media, e-commerce, and virtual assistant apps, among others. In healthcare, machine learning is currently used in disease diagnosis. It provides higher accuracy compared to professional physicians. It is also undergoing extensive research in drug discovery. Another application is robotic surgery, where we have an AI robot helping and performing the surgery with a precision that is actually higher than that of the best surgeons. In transport, Tesla used machine learning algorithms in its self-driving cars. Machine learning is also used for air traffic control. In finance, I worked for 2 years as a KPMG consultant in one of the French banks to develop different machine learning algorithms predicting customer defaults and bank capital requirements. Many banks are currently using machine learning-powered software for fraud detection. Also, banks are using machine learning for algorithmic trading. In social media, I think all social media platforms today use machine learning for both spam filtering and sentiment analysis. Facebook also uses machine learning image recognition. In e-commerce, many online shopping websites such as Amazon, eBay, and Udemy use machine learning for customer support, targeted advertising, and product recommendation. Machine learning is also used in virtual assistant apps. Many startups are founded based on the idea of developing a machine learning-powered assistant in one particular field. This assistant can be a chatbot, for example, which can intelligently reply and answer nearly any inquiries in that field. These are just a few broad and general applications of data science and machine learning. You can develop your own application in any field that you find interesting and have some experience in. And by the end of this course, you will be equipped with the knowledge necessary to create an app in the area of your choice. Let's talk just a little bit about the history of data science. The term data science has been appearing in various contexts over the past 30 years, but did not become an established term until relatively recently. In its early usage, it was used as a substitute for computer science since 1960, when Peter Nauer first mentioned the term. How about the future of data science and data scientists? We can clearly see that the future of data science is very bright. Another evidence for that is the cloud services that have appeared in the last 2 or 3 years. Being extremely cheap and fast, they can help develop more advanced machine learning applications in all fields. So, it will not be surprising to see many tasks that we considered science fiction, such as assistant robots and self-driving cars, already in use in our daily lives. How about the future of data scientists? Let me share some statistics with you. As you can see in the figure on your screen, at the end of 2016, the percentage of jobs for data scientists was 474% larger than those for statisticians. Today, in the USA, the work of a data scientist is one of the high-paying ones. Learning data science may be the best decision you've ever made, and our learning company, AI Sciences, is here to help you achieve this goal. Now, how can you get the ultimate benefit from this course? I highly recommend you take this course very seriously and follow it step by step. We highly suggest that you go through the study materials that you used in your high school, undergraduate, and graduate programs, and revise topics such as linear algebra, calculus, and statistics. We will not go too deep into the math behind algorithms in this course, but we will cover basic ideas, logic, and in some cases formulas to understand our main topic of interest better. Also, try to finish every single project provided in the course on your own, and then check the solution. Finally, we encourage you to go through any further reading material that you will find. It will give you an overview of what you can learn next after finishing the course. Okay, in this lesson, we will explore in detail some important terms in data science. You ready? Let's go. In the following lesson, we will talk more about data and variables. So, what is the data? Data are basically collections of facts, measurements, observations, numbers, words, etc., that have been transformed into a form that can be processed by computers. Data are stored in columns and rows. The convention is that each row represents one observation, case, or example, and each column represents one feature or variable. Got it? We also have 2 types of variables based on their value: numerical and categorical variable. If the value is a number and we can compute the mean for this variable, We call it a numerical variable. But if the value is a factor or label and we can't compute its mean, we have a categorical variable. So we can also talk about dependent and independent variables. A dependent variable is one that we need to predict, and the independent variables, or x variables, will help us to predict a y variable. It is essential to know that x variables need to be independent of each other, and that is why we call them independent variables or predictors. Couple other important terms in data science are population and sample. In data science, the whole population is our target, but due to a lack of resources, a data scientist can't work in the entire population. Because of that, we have to choose a representative sample of the data from the population. The goal of machine learning algorithms is to find parameters that can do the mapping on the whole population based on the given sample. As you can see, we have our population, and we will choose a sample by using the sampling technique. Now, let's talk about outlier and missing data. In data science, an outlier is a data point that differs from other observations. An outlier may occur due to variability in the measurement, or it may indicate an experimental error. Outliers can alter the performance of many machine learning algorithms. As we can see there in the image, we can detect outliers by visualizing the data. In this example, employee number 2 and 19 are outliers based on their profile. How to deal with outliers? We can drop them all together, cap them with a threshold, assign new values based on the mean of the dataset, for example, or apply a transformation on the dataset itself. Okay, one way to handle missing data is by dropping the observations. Another way to handle them is to use data imputation techniques. So if we have a numeric feature, we can replace the missing value with a mean, median, or mode, or we can select random observations from the dataset and replace its feature value in the observation that has missing values. The last imputation technique can be performed by regressing the missing feature on the other features and making a prediction of the missing value. If we have a categorical feature, we can use the mode replacing, or also we can use the KNN model to predict the feature that has a missing value. If you still don't know much about the regression and KNN model, no worries, David will present them to you in the machine learning section. That's it for this lesson. In this class, we will learn about the link between AI, machine learning, and deep learning, DL. You'll find out how a machine learns and the types of learning there are. Ready? Let's go. First, here's the link between artificial intelligence, machine learning, and deep learning. Let's clear the confusion between these three essential terms. So, what are AI, ML, and DL? By looking at the image, it is clear that ML is a subfield of AI, and DL is a subfield of ML. Machine learning algorithms were developed with the goal of finding a useful prediction function. Among machine learning algorithms, let's mention the artificial neural network. An artificial neural network consists of a collection of neurons connected to each other in a specific way. However, the use of neural network was limited because of the lack of computational power and the lack of proper optimization algorithms for neural networks. This is where deep learning came in. It is a simpler algorithm that uses more neurons and layers to perform a lot of learning tasks, like image recognition and natural language processing. Today, deep learning is used in a lot of areas such as the high-tech industry. Tesla, self-driving cars, and the Seattle Amazon store are constructed based on the deep learning algorithms combined with computer vision. Now, let's see how a machine learning algorithm learns. Okay, before we jump into how a machine learns, let us first try to understand how a human baby learns. Think, for example, of a 1-year-old human baby. A baby does not know the difference between an apple and an orange. For him, all fruit is the same: orange, apple, bananas, cucumbers. In his first phase of learning, called phase 1 of learning in the figure, He builds an intuition that oranges and apples are of one shape, and bananas and cucumbers are of another shape. Once a baby is comfortable with the shapes of fruit, he goes into learning phase 2 of learning in the figure, by introducing another property like color. Now he knows that a fruit that is round in shape and red in color means that it's an apple, and a round shape and an orange color means it's an orange. In the phase 3, the baby will gather a lot of data, as shown in the table with these two properties. And based on these data, in the future, he will know the difference between fruits. Machine learning models learn the same way. In machine learning, the properties of the fruit, such as shape and color, are called the features. The fruit type is called the label. Each instant of an input-output pair is called an observation. So depending on the features and labels entered to a machine learning algorithm, learning is classified into 3 main categories: supervised learning, unsupervised learning, and reinforcement learning. We also have semi-supervised and instant-based learning, but in this lesson, we're just going to focus on the main 3 learning types. In supervised learning, we train with labeled observations. That means that for each observation of training data, the input and output are known, as you can see in the image. We try to predict the output from the input by training our machine learning model. Classification is one example of supervised learning where the goal is to classify objects. Regression is another example where we try to understand the relationships among variables. In a glance, in supervised learning, we have the y and the x variables, and we want to make the prediction of y. Okay, now in unsupervised learning, the trainer does not provide a labeled output in the learning dataset. The machine learning algorithm learns from unlabeled data and gathers information from it, as you can see. In short, in unsupervised learning, we only have x variables, and we need to gather the observations in groups based on the information given by x. Unsupervised learning is used mainly for clustering tasks, where we organize the observation into clusters. In reinforcement learning, an agent learns by interacting with the environment. So in this type of learning, the agent performs an action in the environment. This action takes the environment to a new state and gives a reward to the agent. The reward can be negative or positive. From multiple iterations and the rewards, the agent learns based on his past experiences. Reinforcement learning is mainly used in skill acquisition tasks, such as robot navigation or games. Okay, to sum up, we have 3 main types of learning. Supervised, when we have x and y variables. Unsupervised, when we only have x variables. And reinforcement learning. In this case, the algorithm learns by rewards that it gets as a result of its action in an evolving environment. Now you know how a machine learns and what are the different types of learning. I guess now you know a lot more about basic data science and machine learning terms. In this lesson, let me explain some important modeling terms to you. All right, you ready? Let's start. In machine learning, we always split our data into 2. So we have a training data set and a test data set. The training data will help us to train our model, and the test data set will help us evaluate our model performance and accuracy. A typical machine learning model learns from the training data set and applies the learning to the test data set. So if the model is able to make correct predictions on the test data set, then the model is able to generalize the learning to any new data. And then we can say we have a good model. Now, what is an overfitted model? When we obtain a model that works very well on the training dataset but is not able to generalize to the test datasets, we call such a model an overfitted model. In this case, the testing error is large because the model is very complex. The model is underfitted when the training error is large because the model is too simple and just can't capture the true complexity of the data. So, you may wonder, can we control these issues? The answer is yes. The solution for underfitting is either to increase the size of the data set or to increase the complexity of the model. But the solution for overfitting is a bit trickier. The first solution is to gather more data. This solution is not always feasible. The second solution is to use penalty terms in the model, and that is called the regularization technique. And the last one is to make cross-validation. Okay, in short, you need to understand that our goal as data scientists is to come up with a model that is not too generalized and not too focused on training data. This model is called the best fit model. This is basically a trade-off between an underfit and an overfit model, like the middle image. As you're already familiar with overfitting and underfitting, the concept of bias and variance will be very easy to digest. But before we start talking about bias and variance, let us classify the type of model's errors. First, we have the irreducible error, which comes from the nature of the data itself. For example, the noise when you talk through your mobile phone. The second kind of error is the reducible error. We have two reducible errors, the bias error and the variance error. Okay, the bias error is the difference between the average prediction of our model and the correct value which we are trying to predict. The bias error is high if the model is oversimplified. The variance error is the variability of model predictions for the given data. The variance error is high if the model is not generalizing well on new data. Okay, look at the figure at the right. The blue points represent how far we are from the minimum error, which is represented by the small red circle. In the case of low bias, the blue points are not very far from the minimum error. In the case of low variance, the blue points are near each other. Of course, we want our model outputs to be as close as possible to the minimum error, which means low bias and low variance. But it is impossible to have both low bias and low variance. There is a trade-off between bias and variance because as we decrease the model bias, we make it more complex and we increase its variance. And when we decrease the variance, we increase the bias. Looking back to overfitting and underfitting, we can say that when the model is underfitted, it has low variance and high bias. When the model is overfitted, then it has high variance and low bias. As you can see in machine learning, it is important to make a bias-variance trade-off and to choose a middle model. In data science, we have different types and qualities of data, and we need to make them usable in our model. Number one, feature extraction and feature engineering will help us transform raw data into features suitable for modeling. And two, feature selection will help us remove unnecessary features during the data processing step. In this part of the course, we will learn various machine learning models, which are commonly used for prediction, classification, clustering, etc. As I already mentioned, machine learning is broadly classified into supervised and unsupervised learnings. Supervised learning means that the algorithms are supervised during the training phase. So in other words, in order to train these algorithms, we need data that have labeled targets. For example, if a model is being created for predicting house prices, then the historical data that is used to train the model should have a target column stating the price of a house. Unsupervised learning is when we don't have a target labeled data. In this case, the algorithm classifies objects based on some existing features. Supervised machine learning problems have two categories of learning: regression and classification. Regression algorithms are used to identify a relationship between a dependent variable, target, and independent variables, predictors/features. So in regression, the target is always a continuous variable, and the predictors can be continuous or discrete in nature. Regression is best used for finding causal effect relationships between the variables, forecasting, time series modeling, etc. In regression analysis, the model tries to fit a curve to the data points in such a manner that the difference between the data point and the curve is at a minimum. On the other side, we have classification models. The classification models are used to predict the target that has discrete values. For example, class of fruits, orange, pineapple, and lime, or predicting whether a patient is suffering from cancer or not. For this kind of use, machine learning models collect insights from the historical labeled data and use these insights to predict the target class. Okay, listen up, don't forget this. Regression and classifications are all supervised learning models because we have a labeled output, which we need to predict. If this labeled output is continuous, we use regression, and if it's categorical, we use classification. Now, the most used unsupervised learning models are clustering and association analysis. Clustering is the most important unsupervised learning model. It deals with finding a structure in a collection of unlabeled data. So a loose definition of clustering could be the process of organizing objects into groups whose members are similar in some way. I will present clustering in more detail later. Association analysis models discover relationships in large data sets. Hidden data relationships will be expressed as a collection of association rules and frequent item sets with association analysis. Association analysis isn't frequently used. We will not focus on them in this course. What are the machine learning models associated with each of these learning types? I mean, which models are dedicated to regression, classification, and clustering? For the regression purpose, we commonly use linear regression, decision trees for regression, support vector machines for regression, SVR, or neural networks. For the classification purpose, we use logistic regression, decision trees for classification, support vector machines classifier, SVC, nearest neighbor, or neural networks. In unsupervised learning, we use the k-mean clustering. So before we discuss these models in detail, I need to explain the difference between two terms, which can be confusing when you get started in machine learning. The terms model parameter and model hyperparameter. I'll talk more about these two terms in a few minutes, so I think it will be better to explain the difference between these two terms now. A model parameter is a configuration variable that is internal to the model and whose value can be estimated from data. It's required by the model when making predictions, and it is estimated or learned from data. Model parameters are key to machine learning algorithms. They are the part of the model that is learned from historical training data. So some examples of model parameters include the weights in an artificial neural network, the coefficients in a linear regression or logistic regression. On the other side, a model hyperparameter is a configuration that is external to the model and whose value can't be estimated from data. They are often only help estimate the model parameters, and they are often specified by the practitioner. Linear regression is one of the most used supervised machine learning algorithms, and now I'm going to explain what it is exactly, how it works, and show you the logic behind it. First of all, what is linear regression? Let's say that 2 years ago, I made $10,000 on my job, and that last year I earned $20,000. With that in mind, what do you think? How much would I make this year? If you answered $30,000, you just applied linear regression. We make predictions all the time, and most of them follow the logic of linear regression. Linear regression is a machine learning model, which was designed to help you to specify a linear relationship to predict the numerical value of a dependent variable, we will call it y in this course, for a given value of independent variables, we will call them x, by using a straight line, called the regression line. Does that sound complicated? It's not. I'll show you. We can say that linear regression will help us make a prediction based on some information. Prediction equals dependent variable y. Some information equals independent variables x, We use linear regression to answer the following questions. Is there a linear relationship between the two variables, x and y? Which x variable contributes the most? Let's write this model as an equation. It goes like this. Y equals b0 plus bx plus e. b0 is the value of y, even if the value of x is 0. It's called the intercept. B is a coefficient associated to x. It will be a vector of coefficients. E, for error, denotes all remaining information about y that hasn't been explained by the x variables. Of course, the linear model is not perfect, and it will not predict all the data accurately. Okay, we have two types of linear regression, the simple linear regression and the multiple linear regression. In simple linear regression, we use a single independent variable to predict the value of a dependent variable. The model, in this case, will be y equals b0 plus b1x1 plus e. In multiple linear regression, we use two or more independent variables to predict the value of a dependent variable. The difference between the two is the number of independent variables x. Y equals b0 plus b1x1 plus b2x2 plus ... plus e. To keep this lesson simple and to help you understand the rest of the course, right now we will focus on the simple linear regression only. The same thing will be replicated in multiple linear regression. The only thing that will change is the number of x variables. Here are some examples of simple linear regression and multiple linear problems. The estimation of the average student score based on the number of hours they have spent studying, 30 hours. Please note that all the students who pass the exam will receive at least 2 points for their presence. In this problem, the dependent variable y will be the average student score. The independent variable is the hours of study, and it equals 30. The intercept equals b0 equals 1. The regression model we want for the score prediction is score equals b0 plus b1 times hour study. Score equals b0 plus b1 times 30. In this model, the b0 and b1 are coefficients. These coefficients are what we need in order to make predictions about our score. If we add the number of exercises that the student has completed to the model, it will become a multiple linear regression model. Score equals b0 plus b1 times hour study plus b2 times exercises and b plus. For the prediction of the score, we need to estimate 3 parameters, b0, b1, and b2. b0, b1, and b2 parameters need to be estimated based on our historical data. To estimate the linear regression coefficient, we need to minimize the least squares or the sum of individual squared errors. In other words, that's the difference between the actual value and the prediction. The error of the individual I is easily calculated as the difference between the real value of yi equals y hat I. EI equals yi minus y hat I. We square the error for 2 reasons. 1, the prediction can be either above or below the true value, resulting in a negative or positive difference respectively. If we did not square the errors, the sum of errors could decrease because of negative differences and not because the model is a good fit. 2, squaring the errors penalizes large differences, and so the minimizing the squared errors guarantees a better model. Let's look at a graph to understand it better. In the graph, the green dots represent the true data, and the yellow line is a linear model. The dotted red lines illustrate the errors between the predicted and the true values. In practice, we use the OLS algorithm, that's ordinary least squares, iteratively. In each iteration, the algorithm calculates the sum of the individual squared errors. And in the next iteration, the algorithm updates model parameters to shift the line from the previous position to reduce the squared error. Finally, the best OLS estimators of the coefficients are In these equations, x bar and y bar represent the mean. Now, how to make a prediction. We will use the existing data to estimate the values of B0, B1 through BK. We can do that in Excel, R, Python, etc. After that, we can make all the predictions we want. Please note that linear regression is considered to be one of the most straightforward machine learning techniques and an easy model to interpret. But it has its disadvantages. It will only work if the relationship between the dependent and independent variables is linear. That's it. Now you know exactly what linear regression is and how it works. Now present the decision trees model. A decision tree is like a series of if-else conditions that lead to a decision. It can be used for classification or regression use cases. It works for both categorical and continuous input and output variables. Decision tree breaks down a data set into smaller and smaller subsets, while at the same time, an associated decision tree is incrementally developed. The final result is a tree with decision nodes. So consider a scenario where we want to decide whether a loan should be approved for an applicant or not. To decide, we will ask the applicant a series of questions. We might start off with whether the applicant has any other existing loans. If the answer is yes, then the next question might be whether he is a defaulter or not. With this kind of series of questions, we can narrow down the search and make a robust decision. We built the model above by hand to make a decision about whether a loan application should be approved or not. Alternatively, a machine learning model could perform supervised learning using the dataset to arrive at a decision. The decision tree model in machine learning can learn these decisions or conditions from the dataset quickly and build the model. Okay, decision trees have three types of nodes. A decision node has two or more branches. A leaf node represents a classification or decision. We also have the topmost decision node in a tree, which corresponds to the best predictor, called root node. How do decision trees work in practice? Well, that's an interesting question. In practice, there are three important steps in the building of a decision tree. The first one is splitting. A decision tree can have a sub-branch or a sub-tree as well, and the process of creating a sub-branch is called splitting. Have a look at the figure to visualize these notations. So the root node has the full data set, and at each decision node, the test is conducted to split the data set. Decision nodes are executed to split the data until it reaches the leaf node. A leaf node contains a single target value, a single class, or a single regression value. A leaf node that contains only one target value is considered pure. The second one is pruning, or shortening of branches of the tree. Decision trees are prone to overfitting if the parameters are set to favor all pure leaf nodes, which means that all data points in the training dataset are correctly classified. So to reduce overfitting, the following strategies are commonly followed. 1. Pre-pruning, stopping the creation of the tree. And this is achieved by limiting the maximum depth of the tree. So limiting the maximum number of leaf nodes or defining the minimum number of points required to split it further. 2. Post-pruning, just trimming the nodes that contain less information. As you can see, a pruned tree has less nodes and has less sparsity than an unpruned decision tree. Then the last one is the tree selection. In this step, the models are looking for the smallest tree that fits the data. Usually, this is the tree that yields the lowest cross-validated error. Decision tree models work really well if the training data set is in binary format. But this is not a limitation. For continuous features, the decision condition can be applied in the form of greater than or less than a certain threshold. For example, x is greater than 0.7. A prediction on a new data point is made by traversing through the decision tree and checking at each decision node whether the condition is met or not. One of the key factors in the decision tree is entropy. So let me explain to you why. It's important to carefully consider which feature will be used to split each node because decision trees with a different split node may result in different predictions and accuracy. We can utilize a statistical method to identify the feature that should be selected as the root node. The feature that has the most information gain should be selected as the root node. So information gain measures how well a certain feature distinguishes among different target classifications. Information gain is measured in terms of the expected reduction in the entropy or impurity of the data. The entropy of a set of probabilities is H of P in the formula, where P is the probability of outcome event. So if the sample is completely homogeneous, the entropy is 0, and if the sample is an equally divided one, it has an entropy of 1. To understand how entropy and information gain is calculated, let's take a look at the following example. Okay, a training data set has 500 observations. Of these 500 observations, 300 are of positive class, and the remaining 200 are of negative class. Positive class ratio equals 300 divided by 500 equals 0.6. Negative class ratio equals 200 divided by 500 equals 0.4. Entropy of the target variable will be entropy equals minus 0.6 times log 2 0.6 plus 0.4 times log 2 0.4 equals 0.9702. A feature X in the dataset is split as X is greater than 347, 120 positive and 80 negative. X is less than or equal to 347, 240 positive and 60 negative. Entropy of X is greater than 347 equals E1 equals negative 120 divided by 200 log 2, 120 divided by 200 minus 80 divided by 200 log 2, 80 divided by 200. Entropy of X less than or equal to 347 equals E2 equals negative 240 divided by 300 log 2, 240 divided by 300 minus 60 divided by 300 log 2, 60 divided by 300. Entropy of X equals 200 divided by 500 times entropy 1 plus 300 divided by 500 times entropy 2. Information gain for feature X equals entropy total minus entropy of X. Whichever feature in the node has the maximum information gain will be selected for the split. We can also use other indicators like the misclassification rate, the Gini index, and iterative decodimizer 3, ID3, for calculating the information gain of a feature. What are the hyperparameters of this model? Pre-pruning parameters are the main hyperparameters of a decision tree model. For example, the maximum depth of the tree, the maximum number of leaf nodes, and minimum number of data points required to split the node further. A combination of these hyperparameters can be used to build the decision tree, which is generalized over the dataset and provides good accuracy. What are the advantages and the disadvantages of a decision tree? Decision trees are computationally cheap to use, easy for humans to understand results, and it can deal with irrelevant features. Its disadvantages are it is prone to overfitting and provides poor generalization performance. Sometimes it gives low prediction accuracy. Pruning and post-pruning strategies are implemented in decision trees to reduce overfitting, but still, decision tree models tend to overfit. So to overcome this, data scientists use an advanced modeling technique called Ensemble. The idea of Ensemble is to build many trees, all of which predict well and overfit in their own way, and average the results to reduce overfitting. Ensemble means assembling many machine learning models to create a more powerful and robust model. These machine learning models, also known as Bayes estimators or Bayes learner because they are combined together. The most popular ensemble techniques are bagging and random forest. Bagging combines sampling techniques and aggregation to form an ensemble model. In practice, multiple samples are chosen randomly with replacement within the training dataset. Let me explain how the sampling is made. So suppose that a sample of 10 observations is drawn from a training dataset of 100 observations. These observations are then returned to the training dataset before another sample is drawn. So the next sample of 10 observations is drawn from a training dataset of 100 observations. In simple terms, at any point, all of the training dataset observations will be available for a sample to be drawn. This sampling technique is called the bootstrap. For each of these samples, a decision tree or other Bayes learners is created. Finally, these decision trees or Bayes learners are aggregated to achieve an efficient predictor. Typically, the combined estimator is better than any one of the single decision trees. Question: how does the algorithm choose the output at the end of this aggregation? Okay, the output is chosen based on voting for classification or on an averaging for regression. Now, how about the random forest model? So you learned how bagging works. Random forest also uses the same bagging technique with a slight modification. During bagging, all features of the training dataset are used on sampled data to create the decision trees or the Bayes estimators. Because of this, sampling techniques used in bagging the datasets in each sample are quite similar. Each Bayes estimator usually breaks at the same feature. This results in quite similar Bayes estimators. This means that weak features will not be incorporated. To avoid this, in random forest model, the samples are created with a subset of features selected randomly for each node in the decision tree. This selection of a subset of features is repeated separately in each node so that each node in a tree can make a decision using a different subset of features. This process of randomly selecting sampled data and a number of features for a split at each node ensures that all decision trees in the random forest are different. Similar to the decision tree, the random forest also provides feature importance, which is computed by aggregating feature importance over the trees in the forest. Typically, the feature importance provided by random forest is more reliable than the one provided by a single tree. The maximum number of features to split at each node determines how random each tree is, and a smaller value reduces overfitting. As a rule of thumb, this parameter can be set to the square root of a number of features for classification and for regression use cases. Criterion, Gini, entropy, number of decision trees, maximum number of features, maximum depth of the decision tree, minimum number of samples required at each leaf node, minimum number of samples required to split a node, and maximum number of leaf nodes in each decision tree are all hyperparameters of ensemble models. This hyperparameter can be tuned to get a generalized and accurate machine learning model. Benefits of random forest. Okay, what I can say is that ensemble models are very powerful and often work without parameter tuning. But the bad news is it is difficult to understand thousands of trees and explain the decision-making process. That is why this model is considered like a black box. Another disadvantage is that ensemble methods need more computing resources and take more time to learn from data. Okay, another machine learning model is boosting. Boosting is another model that makes a base estimator like decision tree more powerful by making a sequential execution, and each subsequent estimator focuses on the weakness of the previous estimator. Boosting incrementally builds an ensemble by training each model with the same data set, but where the model coefficients of estimators are adjusted according to the error of the last prediction. Several weak models team up to produce a powerful ensemble model. The main idea of boosting is to focus on the observations that are hard to predict. Boosting can reduce bias without incurring higher variance. Here are the popular boosting algorithms: eta boost and gradient boosting. Let me explain to you how they work. Eta boost is adaptive boosting, where more attention is given to the records that are not correctly predicted. After each iteration, weights of the wrongly predicted observations are increased so that these records will be picked up more in the next iteration to gain better accuracy. Gradient boosting is another popular boosting algorithm. It works by sequentially adding the previous predictor's underfitted predictions to the ensemble, ensuring errors made previously are corrected. Here's what you need to know. Boosting does not introduce randomness to the decision trees or any based learners. However, it uses strong techniques to build accurate predictors. In most cases, the maximum depth for boosting models is kept to 5 models. This makes the model faster and the model consumes less memory. The hyperparameters for these models are the number of decision trees, maximum depth, and learning rate. A lower learning rate means more trees are required, and a higher learning rate means less trees are required to build a model. These hyperparameters should be tuned to get an optimized machine learning model. Boosting models are more sensitive to hyperparameters, but once the hyperparameters are tuned properly, these models provide very good accuracy and generalization. So in general, ensemble models are very powerful and widely used. However, like the bagging models, it is difficult to understand thousands of trees and explain the decision-making process. I just don't recommend it for dimensional sparse data. They don't do very well in high-dimensional data. Well, the SVMs model, or support vector machines. Support vector machines are one of the supervised learning algorithms mostly used for classification tasks. However, SVM algorithms can be used for regression as well. A support vector machine for classification is called the Support Vector Classifier, SVC, and for regression it's called the Support Vector Regressor, or SVR. SVMs are based on the idea of finding a hyperplane that best divides a dataset into 2 classes, as shown in the image below. You may ask what the hyperplane is. Okay, take this example. Say we want to classify a task with only 2 features. You can think of a hyperplane as a line that linearly separates and classifies our data in 2. Intuitively, the further from the hyperplane our data points lie, the more confident we are that they have been correctly classified. We therefore want our data points to be as far away from the hyperplane as possible, while still being on the correct side of it. So, when new testing data is added, whatever side of the hyperplane it lands on will decide the class that we will assign to it. Now, how do we find the right hyperplane? Or in other words, how do we best segregate the 2 classes within the data? Before we answer this question, we need to understand what is a margin. A margin is equal to the distance between the hyperplane and the nearest data point from either set. Now, the goal is to choose a hyperplane with the greatest possible margin between the hyperplane and any point within the training set, giving a greater chance of new data being classified correctly. As you can see in 2 dimensions, it is very easy to classify using SVM. But sometimes it's harder to identify clearly the hyperplane because the data is rarely ever as clean as our simple example above. A dataset will often look more like the jumbled balls which represent a linearly non-separable dataset. Look at this case. In order to classify a dataset like this one, it's necessary to move away from a two-dimension view of the data to a three-dimension view. Explaining this is easiest with another simplified example. Imagine that our two sets of colored balls above are sitting on a sheet, and this sheet is lifted suddenly, launching the balls into the air. While the balls are up in the air, you use the sheet to separate them. This lifting of the balls represents the mapping of data into a higher dimension. This is also known as kerneling. Okay, because we are now in three dimensions, our hyperplane can no longer be a line. It must now be a plane as shown in the example. The idea is that the data will continue to be mapped into higher and higher dimensions until a hyperplane can be formed to segregate it. So that's how SVMs work and produce the output. So, what are the benefits and the disadvantages of SVMs? SVMs can give a great accuracy and can work well on smaller, cleaner datasets. Nevertheless, if you have a larger dataset, it isn't suited as the training time can be very high. Another machine learning algorithm is the k-nearest neighbors, KNN. The k-nearest neighbors, KNN algorithm belongs to the family of instance-based competitive learning and lazy learning algorithms. It's a lazy learning algorithm because the calculation is delayed until a prediction is required. It is called a localized model because only the data points that are near new data points are used for model calculation and for predicting classes of new data points. So let me explain how this works. When a prediction is required for an unseen data point, the KNN algorithm will search through the training dataset for the k most similar neighbor. The prediction attribute of the most similar data points is summarized and returned as the prediction for the unseen instance. So in this model, k is the number of neighbors we want to check to classify a new data point. If k is greater than 1, the model uses voting to classify the new data point. In short, the class that is in the majority is assigned to the new data point. For example, so if the value of k is set to 3, the model will check the 3 nearest data points to classify the new data point. The default value of k is 1, which means that the vanilla KNN model classifies the new data point according to the class of the nearest neighbor. The yellow and purple circles represent the data points from the training dataset, and we want to predict the class for the red data point. If the value of k is set to 3, then the model will check the 3 nearest data points, inner circle, and then classify the red data point. If the value of k is set to 6, then the model will check for the nearest 6 data points, outer circle, and then classify the red data point. In the figure above, the red point will be classified as follows. If k equals 3, Class B, 2 votes for Class B, and 1 vote for Class A. If k equals 6, Class A, 2 votes for Class B, and 4 votes for Class A. In a multi-class data set, we count how many data points belong to each class, and the class that is in the majority is predicted for the new data point. So, how does the algorithm choose the nearest points? The KNN uses the distance to evaluate which point is near to the new data. For continuous features, Euclidean distance is calculated, and for categorical features, another distance called Hamming distance is calculated. The important hyperparameter for KNN is the number of neighbors. It holds the value of k. The default value of this parameter is 5. K-nearest neighbor has a lot of benefits. Among them, its simplicity and flexibility. It also works well with enough representative data. The problem that we can face sometimes is that the KNN algorithm is space-consuming, because for each prediction, the calculation is done separately. First of all, logistic regression is among the most commonly used and best-known algorithms that we can use to solve a classification problem. It's named logistic regression because of the logit function. which is used in this method of classification. Other than that, logistic regression is pretty much the same as linear regression. The purpose of logistic regression is to detect a relationship between features and find the probability of a particular outcome. In a way, it extends the idea of linear regression to a situation where the outcome variable is categorical. For example, let's try to predict whether a student will pass or fail an exam. The number of hours spent studying is given as a feature, and the response variable has two values, passed and failed. Okay, in the equation below, you can see that we need to predict the y variable, which can take two values, 0 or 1, 0 for failed and 1 for passed. It turns out that it is virtually impossible to predict y with the following model. Y equals b0 plus b1 x1 plus ... bk xk. That's because y is a categorical value, and b0 plus b1 x1 plus ... bk xk will give a continual value as the result. Therefore, instead of predicting this categorical variable, we're going to predict the probability of the realization of y equals 1. P equals probability of y equals 1. In order to do that, we need a link function. The logit link function. Okay, a link function is basically a function of the mean of the response variable y that we use as the response instead of y itself. It means that when y is categorical, we use the logit of y as the response in our regression equation instead of just y. The logit function is the natural log of the odds that y equals one of the categories. For mathematical simplicity, we're going to assume y has only two categories and code them as 0 and 1. P is the probability that y equals 1. So, for instance, those x's could be specific hours spent studying, number of completed exercises, and the score in the first exams, while P would be the probability that a student would pass an exam, as in our first example. Linear regression versus logistic regression. Instead of linear regression, the line between y and x, the relationship between x and the probability P, is a logistic distribution. How to estimate the logistic regression coefficients. At this point, we don't know the coefficients, B0, B1, Bk of the model, so we must estimate them in order to make predictions. Unlike the linear regression model, logistic regression uses ordinary least square for parameter estimation. The estimation is done by using maximum likelihood, due to its more general nature and statistical features. There can be an infinite set of regression coefficients. The maximum of the log likelihood estimate is that set of regression coefficients for which the probability of getting the data we have observed is maximum. In other terms, we must make estimates for the coefficients that predictions are as close as possible to the originally observed value. So, how to make a prediction? Well, the prediction is made using the original logistic function and the estimated coefficients from the maximum likelihood function with the observed data to compute the estimated probability of P. If the probability of P is below 0.50, the predicted value of y is 0. Otherwise, it will be 1. In our example, the student will fail based on the value of x. In the figure, we make a prediction by using a different set of x variables. The first set gives us a red point with p equals 0.29. In the first case, the value of y is equal to 0, as the predicted value of p is less than 0.50. In the second case, the green point, p equals 0.90. The predicted value of y will be 1. Compared to other models, logistic regression is rather simple and efficient. However, it can't handle a large number of categorical variables successfully. That's it. Now you know exactly what logistic regression is and how it works. In our next tutorial, you'll learn how to apply it in Python and R. Click on the video above to see this tutorial. Thanks for your time, and hey, if you like our videos, please like it, share it, and subscribe to our channel. Oh, and click on the notification button. so you can receive notifications for our next course. Enjoy machine learning. First, though, let's see what a neuron is. A neuron in the neural networks field is something that takes some input, applies some logic, and outputs the result. We call it a function. For example, if we have f(x) equals y, x is the input and y is the output, and f is a function. To illustrate, so let's say I'm trying to understand the relationship between the length of the video we produce on our channel and the time that people actually spend watching the video. We collect data from some of our videos. We have the video duration, let's call it x, and the watching time, let's call it y. And we imagine there is some relationship between them, denoted by f. After that, I inform the machine about the relationship I expect to see between these two variables. I can choose a linear function between x and y, or a nonlinear function. This function is what we call a neuron. Then we can predict the time people would spend watching a video lesson precisely based on our neuron and the video duration. Now, let's see what a neural network is. Well, in one sentence, a neural network is a network of neurons. It means that we have many neurons and all their inputs and outputs are intertwined and they feed each other. In this figure, you can see the difference between a neuron and a neural network. As you can see, a neuron is a basic unit of learning and a neural network is a bunch of interconnected neurons. Neural networks help us cluster and classify. They help to group data according to similarities among the example inputs, and they classify data when they have the output variable in the existing data set to learn from it. The questions you may ask at this point will probably be: question 1, what kind of problems do neural networks solve? Neural networks could be applied for spam filtering, fraud detection, customer relationship management, angry customers or happy customers, image recognition, self-driving, etc. Question 2, which functions will I use in each neuron? We can use linear or nonlinear depending on the complexity of the problem. Question 3, what is the architecture of the network? We have different types of neural networks: a perceptron, a recurrent neural network or RNN, a convolutional neural network, CNN, etc. Now, how we can run our neural network. In the first place, the neural network learns to recognize patterns, just like a human. We show them examples of correct inputs and outputs in the hope that when we give it a new example input that it's never seen before, it will know how to give the correct output. That's what we call training on existing data sets. Don't forget, machine learning equals learning from examples. Let me present you the most basic neural network, the perceptron, and discuss how it processes inputs and produces an output. So suppose we use our neural network for fruit image recognition. I have two inputs for that purpose: the color and the shape of some fruits in our data sets, and a single binary output, which is the fruit name. Once the machine has learned all these properties, I can give it a new image of a fruit, one it hasn't seen before, and it will hopefully classify it correctly and be able to tell me whether it is an orange or a banana. The perceptron learns from the existing data and knows which information will be most important in decision making. To decide between multiple information, it uses something called weights. The weights are just numerical representations of these preferences. A higher weight means our perceptron considers that input more important compared to other inputs. So for our example, let's deliberately set suitable weights for our two inputs: 2 for the fruit shape and 4 for the fruit color. Now, how does the perceptron calculate the output? It simply multiplies the input with its respective weight and sums up all the values it gets from all the inputs. Let's consider that we have two shapes, round and long. If the shape is round, the input 1 value is 1, and if it's not round, the value is 0. We'll repeat the same thing with the color. red takes the value of 1, and the yellow color the value of 0. Based on this information, if the fruit is round and red, our perceptron would do the following calculation. Total equals round times shape weight plus red times color weight. So total equals 1 times 2 plus 1 times 4 equals 6. This calculation is known as a linear combination. Now let's see what this value 6 means. We first need to define the threshold value. Because the perceptron's output is either 0 or 1, 0 for a banana and 1 for an orange, this output is determined like this. If the value of the linear combination is higher than the threshold value, then the output is 1, and if it is not, the output is 0. So let's say the threshold value is 3, which means that if the calculation gives you a number less than 3, we have a banana. But if it's equal to or more than 3, then we have an orange. That's how perceptron works. It uses a linear combination and produces the output. In reality, we set the weights to random values, and then the network adjusts those weights based on the output errors it made using the previous weights. That is called training the neural network. In the mathematical language, the perceptron algorithms work like this. The output is equal to 0 if the sum of the weight times the value of the variable is smaller than a threshold. In the same way, the output will be equal to 1 if the sum of the weight times the value of the variables is bigger than a threshold. To make things just a little simpler for training, the threshold is sometimes moved to the other side of the inequality and replaced with what's known as the neuron's bias. Now, with bias, we only need to make changes to the left side of the equation, while the right side can remain constant at 0. The left side of the equation is a function. It is a function that transforms the values or states the conditions for the decision of the output neuron. It is known as an activation function. The formula above is just one of several activation functions, and the simplest one, used in deep learning, and it is called the heavy-side step function. In reality, we can also use other activation functions. For example, we can use the sigmoid function, the tan function, and the softmax functions. Each of them has a purpose, and we'll present each of these functions in a special video dedicated just to that. That's it for our first introductory video on neural network. Now, you have a solid understanding of the basics of neural networks and how perception works. In our next video, in neural networks, we will explain how the multi-layers perceptron works, and we will present the concept of hidden layers. Okay, now let's present an unsupervised machine learning model, the clustering in general and the k-means clustering in particular. Clustering models are used to analyze unlabeled data and get useful insights from it. Clustering is equal to grouping things, means the data points which are similar in some way and different from other data points are grouped together. Each group of the data points is known as a cluster. In the example, data points are divided into 4 clusters based on the geometrical distance between 2 data points. The data points which are close to each other are assigned to one cluster. This approach of creating clusters is known as distance-based clustering. Another approach of creating clusters is the conceptual clustering. In this approach, clusters are based on conceptual similarity. So, for example, in a dataset of oranges and apples, 2 clusters will be created, one for all apples and another one for all oranges. This approach uses properties of data points to distinguish one data point from another and to group data points with similar properties together. Clustering is a very subjective area of discussion. It is difficult to determine how one clustering is better than the other one. Machine learning algorithms learn the insights from the data and apply these insights to create clusters. Since we don't know those insights, it is hard to say the clustering done by the machine learning model is best or not. So the user must provide an appropriate criterion to get suitable clusters as an output from the machine learning model. Consider a data set that contains green color balls, red color balls, green color apples, and red color apples. Now, if we provide color as the clustering criteria to the machine learning model, then it will create two clusters. One of the green color balls and green color apples, and the second one, of course, of red color balls and red color apples. However, if the criteria provided is edible, then the machine learning model will create two clusters, one of all apples and another one of all balls. Clustering algorithms can be applied in many industries. Marketing, like finding groups of customers with similar behavior or customer segmentation. Biology, for plants classification. Insurance, fraud detection. City planning, earthquake studies, document classification, identifying crime localities, cyber profiling criminals, etc. Now, let me explain to you how k-means clustering works. K-means clustering is one of the most useful clustering algorithms. It tries to find cluster centers that represent certain regions of the data. K-means clustering is a two-step process. 1. Assign each data point to the closest data center. 2. Set the cluster center as the mean of the data points assigned to the cluster. The algorithm keeps on executing these two steps until the assignment of data points to clusters no longer changes. Once we decide how many clusters are required, the number of clusters is passed to the algorithm. So let's say for a given data set, we want 3 clusters. In the initiation step, the algorithm randomly selects 3 cluster centers. Each data point is assigned to the cluster center it is closest to. We then update the cluster center with the mean of the cluster. The previous 2 steps are repeated until the assignment of data points to clusters no longer changes. Clustering is similar to classification. The only difference is that classification use cases have labeled data. The classes are defined and clustering creates various clusters or classes from the dataset. One of the major benefits of the k-means algorithm is the implementation. K-means is a relatively efficient method. However, we need to specify the number of clusters in advance, and the results are sensitive to initialization and often terminates at a local optimum. Unfortunately, there's no global theoretical method to find the optimal number of clusters. A practical approach is to just compare the outcomes of multiple runs with different k and choose the best one based on a predefined criterion. In general, a large k probably decreases the error but increases the risk of overfitting. In the previous part of our course, we learned the basics of data science and machine learning and the most important machine learning models. In practice, we can apply, manually or automatically, various models on a given data set before finalizing and choosing the right model and the more efficient one. But how do we evaluate the performance of a model to determine the one model that is performing better? In this part of the course, we will answer this question by presenting some performance indicators to evaluate the model. Let's start with the R-squared. R-squared is the most common way to evaluate the performance of a linear model. It is a statistical measure of determining how close the data is to the fitted regression line. It is a proportion of explained variance to total variance. R2 equals explained variance over total variance. You can see how it's represented graphically here. Typically, the R-squared value lies between 0 and 1. 0 means the model does not explain any variability of the data around its mean. 1 means the model explains all the variability of the data around its mean. So the higher the value of r squared, the better the model fits the data and better the model explains the variance of the observed data around its mean. However, it is difficult to tell whether an increase in the r squared value is a result of better model performance or more features in the model. That's why in multiple linear regression, it is better to choose the adjusted r squared. Adjusted r squared is a modified version of r squared that has been adjusted for the number of features in the model. Adjusted r squared penalizes the r squared if the choice of the feature newly added to model is not good. So in classification scenarios, having good r squared or adjusted r squared values is not important until both the classes are unidentified with similar accuracy. This becomes a big issue when the data is not equally distributed for the targeted classes. Okay, for example, consider a dataset with 98% observation of class A and 2% observation of class B. The model can easily get 98% training accuracy by simply predicting that every sample belongs to class A, but the prediction accuracy for class B is very poor. To overcome this situation, model performance should be evaluated for each class and then aggregated to get the overall performance of the model. Confusion matrix provides the right tools to get the individual and overall performance of a classification model. So let's take this example with two class, positive and negative classes. In the figure, we have the classifier, the prediction outcome, and actual values. The total number of positive classes is P, and the total number of negative classes is N. TP, true positive, in the top left corner of the figure equals actual classes positive and predicted classes also positive. This states how many positive classes correctly predicted. This is also known as the power of the model. Fn, false negative, in the top right corner of the figure, actual class is positive and predicted class is negative. This states how many positive classes are predicted as negative. This is also known as a type 2 error, miss. Fp, false positive. In the bottom left corner in the figure, actual class is negative and predicted class is positive. This states how many negative classes are predicted as positive. This is also known as a type 1 error, false alarm. Tn, true negative, in the bottom right corner of the figure, actual class is negative and predicted class is negative. This states how many negative classes are correctly predicted. So, correctly predicted classes is equal to TP plus Tn. Incorrectly predicted classes is equal to FP plus Fn. Actual positive classes is equal to P equals TP plus Fn. Actual negative classes is equal to N equals FP plus Tn. So we compute the proportion of records that are correctly classified, called the accuracy of the classification model, and it is calculated as follows. Accuracy equals TP plus Tn over TP plus Tn plus FP plus Fn. So another important validation technique is the cross-validation. Cross-validation is a tool that utilizes the training data set in a better way to reduce overfitting and underfitting. It is a model validation technique for assessing how the results of statistical analysis will generalize to an independent data set. The purpose of using cross-validation is to increase confidence in the model trained by the training data set. So without cross-validation, our model may perform well on the training dataset, but their performance decreases when applied to the testing dataset. The testing dataset is precious and should only be used once, so the solution is to separate one small part of the training dataset as a test of the trained model, which is the validation dataset. Okay, here are two cross-validation techniques. K-fold cross-validation. This involves splitting the training dataset into K subsets of data, also known as folds. The machine learning model is trained on K1 subsets and then evaluated on the subset that was not used for training. This process is repeated K times, with a different subset reserved for evaluation and excluded from training each time. So once the model has been executed for all training subsets, the average of error in each run is calculated and represented as the cross-validation error. Leave one out cross-validation. This is another technique used for cross-validation. It's a logical extreme of K-fold cross-validation, where K equals N, the number of observations. So for each run, only one observation is left with a validation dataset. This approach leads to higher variation in testing model effectiveness because testing is done against one observation only. Hence, the estimation is highly influenced by the validation observation. If the validation observation is an outlier, it can lead to higher variation. At this last part of the course, I will give you some best practices in data science and machine learning. Okay, you need to be aware that the data set that we will get for machine learning problems is not always as clean as we can expect. We might have to clean the data set and transform it into a data set that can be used to build a model. For this purpose, we might have to go through multiple processes like data processing, feature engineering and feature extraction, feature scaling and selection. This set of processes is a major part of a machine learning project because the model performance is based on the data on which the model is trained. Garbage in, garbage out. We already talked a little bit about feature engineering and feature extraction. I'm going to give you some best practices that we can follow to tackle the datasets and machine learning use cases. Another important concept is one-hot encoding. Machine learning cannot handle non-numeric features by themselves. So the question that you may ask is, how do we transform the non-numeric features? Let's take our example in the employee salary. Suppose that in the dataset, gender is maintained as a non-numeric feature, and this feature can have two values, male or female. For an organization, an employee's gender is meaningful information. Since it is a non-numeric feature, if we try to train a model on the gender feature, then the model will not be able to interpret anything meaningful from it. To make the gender column meaningful to the model, we must transform it into a numeric column. One-hot encoding is one of the transformation techniques that can be used to transform categorical features into numeric categorical features. So if the feature has only two categories, then those two categories can be replaced by 0 and 1. In our employee dataset example, we can replace male with 0 and female with 1. Now, consider a scenario where the categorical column has more than two categories. In other words, in our dataset, gender have three values, male, female, and unknown. So one-hot encoding can be extended to take care of this multi-category features. It creates a new feature for each category, and for each observation, the value 1 will be assigned to the newly created feature to which the category belongs to. Other newly created features will be set to 0. For example, in our employee gender example, 3 new features will be created like in the table. Binning. In a few machine learning scenarios, continuous features cannot be used directly to train a model. These features should be converted into categorical features, and then one-hot encoding should be applied to make these features important for the machine learning model. In our employee dataset example, employee age ranges from 21 to 60 years. These employees can be categorized into 4 age brackets: 21 to 30, 31 to 40, 41 to 50, and 51 to 60. The technique of converting a continuous feature into multiple bins and creating a new feature from it is known as binning or bucketization. It's also known as quantitization. Binning transforms a continuous feature into a categorical feature, and categorical feature engineering might need to be performed before using this feature in modeling. We can create a new age group feature and map each employee with one of these brackets. For binning, we can use the domain expertise as well as a few statistical methods to correctly determine the number of bins/buckets and the boundaries for each bin. So some of the common methods of binning are 1. Fixed width binning. In this technique, width is decided for each bin based on domain knowledge, rules, or constraints. 2. Quantile-based binning. This technique divides the data into Q-equal partitions. If Q equals 4, then the parts are quartiles. Divide data into 4 equal partitions. 3. Two-way ANOVA, analysis of variance test. This is used to find similarity between the various data points of the feature. These similar data points can be grouped together to partition the dataset. First, let's discuss what feature engineering is. Features are the independent variables. Don't forget, we will use this term a lot, feature. Feature equals variable. Once again, independent variables or features are used to predict the dependent variable. Frequently, these features have hidden information that the machine learning models cannot utilize. To negate this situation, in the data pre-processing stage, we just apply the domain knowledge and create new informative features out of the existing features available in the dataset. These features should be created carefully, though, otherwise the model may overfit. The set of features on which the model is supposed to run should be selected wisely because good features with good quality data can yield a less complex model with better results. Feature engineering is a recursive process that can be divided into the following steps. Understand dataset, brainstorm features, create new features, validate what impact these features have on the prediction result, restart from step 1 until the desired accuracy and other metrics are achieved. So, for example, consider a model designed to predict salary hikes for employees in an organization. The dataset contains employee ID, geographical location, date of birth, employment start date, career start date, etc. In this dataset, date of birth and career start date might not be useful for a dataset. If we derive 2 new features, for example, employee age and years of experience, these 2 features could play a key role in salary hike prediction. The process of identifying and creating these derived features is called feature engineering. In reality, though, feature engineering is an art, and it comes with domain knowledge and experience. Feature scaling. Some machine learning algorithms do not perform well when all features in the dataset are not on the same scale. So coming back to our employee dataset example, salary may range from $40,000 to $200,000, and age ranges from 21 to 60. These 2 features do not have the same scale. Rescaling these features can improve the performance of some machine learning models. Now, how we can make feature scaling. We have 2 common techniques for feature scaling. The first one is normalization. This technique transformed the feature into a 0 to 1 scale. The great thing about normalization is to reduce also the effect of outliers. The new value of the feature called x changed is equal to the value of x minus the minimum x value and dividing by the maximum x value minus minimum x value. X changed equals x minus x min over x max minus x min. The second one is standardization, which transforms the features so that the mean of the distribution becomes 0 and the variability becomes 1. Standardization is not significantly affected by outliers. Look at the figures below. They show how the transformed feature will be after implementing normalization and standardization. Well, that's it for this free AI Sciences course. Hopefully, this course has demystified the notion of data science and machine learning. That is just the beginning. So now that you are familiar with the logic behind the different types of learning, you know how to create simple models, it's time to move on. But you will not be alone on that path. We have more content, courses, and books to reinforce your efforts and guide you at every stage. Machine learning is a crucial development in today's world. The concepts behind it have been around for more than a decade, but the age of machine learning and related models, such as artificial intelligence, data science, and more, is now. The change is just happening, and it is fast. You've made a great decision to start your journey into the world of machine learning with this free course. Today, the knowledge and the ability to use machine learning is a competitive advantage. Tomorrow, it will be a mere necessity. Machine learning techniques have already started to change the world of business by creating a new value for data. The future will be even more exciting. Very soon, most of the devices and apps that we use daily will be fueled by machine learning algorithms. Many of them already are. Now, though, you have a chance to become a part of this major development. Congrats on your decision, and don't forget to check out our courses, ebooks, and contents. Now, as I promised you, there is a gift for you. It's an ebook available online where you will learn about machine learning. You can find it at this link, https://www.aisciences.net/gift-ebook-machine-learning. We highly recommend that you visit our website, aisciences.net, and subscribe to our email list. You will receive all of our books free in an ebook format, and you will be informed about all our promotions and offers. If you have any feedback, please let us know by sending an email to review@aisciences.net. This feedback is highly valued, and we really look forward to hearing from you. If you enjoyed this video, please like it, share it, subscribe to our channel, AI Sciences, and make sure you click on the notification button so you can receive a notification when our next course is ready. See you at the next video.